Cool. So let's review trees a little bit. So a tree is a data structure. So if you're really into horticulture, um, came to the wrong place. Horticulture, right? That's the plant plant stuff. I'm not sure. Anyways, um, anyways, cool. So a tree is a data structure. It's very common. It's a hierarchical organization of data where if you think about a list, a vector, an array, these are sort of linear sequential organizations of data. A tree is the idea of like things are on top of other things. So like you constantly branch and branch and branch, which is why you have a very high efficiency with trees compared to other things, right? But the disadvantages is that it can be a little bit more complicated to program, and you can get into situations where a tree just becomes a linear list, and you have to kind of avoid that and do things to ensure that your hierarchy is maintained. So, to kind of talk a bit about the terminology, with a tree you have a root node. So this is the node that kind of spawns everything else off. There are edges between nodes in the tree, right? So a root has two edges to its two children in this case. You also measure the level, the depth of a tree, where level 0 is your root, level 1 is 1 depth, level 2 is two levels of depth, and a path is the path you would take to go from a particular root node to a given leaf node or node inside of the tree. And a leaf node is just a node with no children. So we just went through this, and also we should add that traversing a tree, or the traversal of a tree, is passing through all of the nodes in a given tree in a given order. So min max, or depth first, or breadth first, whatever. Oops. Cool. So a binary search tree is the most common one, where you limit the number of children by 2. So you have a left and a right node, generally speaking, or top, min, max, or whatever you want to call it. And usually the higher values go into the right, the lower values go into the left. So a very simple kind of binary tree is the value to your left is less than the parent, the value to the right is greater than the parent. Which is a bit different than a heap. Right? We've talked about heaps, and a heap is a kind of tree, but in this case, we're not doing the lesses. Basically, both children are less than the parent, or greater than the parent, based on whether or not you're doing a min or max heap. So this is a little bit different. You can kind of think about it like this, right? And the node class is quite simple, where you have your data. In this case, it's an integer. And you have your left node and your right node, which is just a pointer to your own data structure. So it's quite an elegant data structure. So to create a tree class, we need to have something to wrap it, obviously, but an insert method and a traversal method. We should also eventually add remove methods and things like that. But for the most part, let's just take a look at these. And this is a recursive data structure, or an algorithm. The algorithm associated with this data structure is recursive, and that's one of the reasons that trees are so powerful. So with very little code, you can do some pretty powerful things. So first, insert. There's 3 different scenarios. There's a scenario that the tree is empty, so you just set it as the root. There's the case that you are the value is less than the node, so then you would set it to as a child. Or you would then move down to the child and then do what you got to do. It's a recursive kind of thing. So when you insert, you don't just add it to the child, because you might have a child there. So you would go down to that and then apply the same algorithm until you get to a node that doesn't have children, or doesn't have a child in the lesser category. And then you do the same, or you do the same thing with the greater scenario. So you can kind of find your way down to the next available spot. So the traversal of a tree, there are a number of different ways, and funny enough, this is just about what you do first in the recursive algorithm. So if you do it pre-order, right? What you would do is you would list the value of the node, and then the left node, and then the right node, and then you would keep doing, and then you would keep doing that. And for the left node, you just recurse. For an in order, you would list the left node, then the current node, and then the right node. And keep in mind, when you list the left node, you then apply this algorithm to the left node, right? And then post order for the given node, you list the left nodes, the right nodes, and then your data. And based on this, so for example, if we write our value for the pre-order, we would then write our value, the root node, and then we'd go down to the left node and iterate through that, right? So we'd then get the left node, and then its value, and so on. And the way you do this, actually, you get different kinds of orderings, right? In this case, you get the order in which, generally speaking, pre-order, like the, yeah, if you want to get the actual order of the nodes, in order, as in the sorted values, then you want to use the in order, where for the given node, you first print out everything that's less than the current value. So you go left, then your own value, and then everything greater. So this is the in order code, and as you can see, all you would have to do is move these lines around to get the different pre-order or post-order scenarios. So it's actually quite elegant. So for example here, if we were to do the in order ordering, what we would get is first we go 23, and then we'd go to the left. Sorry, we would not print 23. That's pre-order. If we wanted to do, first we go left to 13, and we go left again to 7. We'd print 7, then we pop up to 13, print 13. We go back down to 18, again greater than, and we print 18. Now we pop up to 23, we print 23. We would then go to greater than 33, and then greater than that 47, right? And to go kind of review, like fast replay, we would get then 7, 13, 18, 23, 33, 47. That's in order. The pre-order, what we would do is we'd first go through our own node. So we'd go 23, we'd print 23, and we'd go down to 13. We'd print 13. We'd go down to the left and print 7. No more leaf nodes. We pop back up, and then 18, and then pop back up, and we go 33, and then 47. And so that would look like just a fast replay: 23, 13, 7, 18, 33, 47. So, and then post order, you would have, what is the post order again? Yeah, you would have your left. So you'd go left, left, 7, right, then 18, then 13, and then 23, no, and then 33, then 40, no, then 47, 33, and then 23. So kind of fast replay, you'd go 7, 18, 13, 47, 33, 23 for the post order. I don't exactly know what the other ones are used for, because often you would also use what's called depth first search or breadth first search, which utilize a queue and a stack, which we'll see in the graph segment. For a depth first search, what you do is you basically, you just do what we just talked about, which is you add to a stack the children, and then with a breadth first search, you would do the same with a queue, similar ideas. And that way, with breadth first, you're actually you'd go like 23, 13, 33, 7, 18, 47. With depth first, you're actually going to be doing 23, 13, 7, 8, 23, with depth first, yeah, 23, 13, 7, 18, 33, 47. So it's like, there's a lot of different ways, but often you want to have the same level, like a breadth first search, which is really nice, and that you would get 23, 13, 33, 7, 18, 47. So like, this is one of the reasons that trees don't have like a standard implementation. Like you'll find vector or list or whatever in the STL, but often you won't find a tree. Associated arrays and dictionaries tend to use trees. That's the most efficient way to do them. But one of the reasons is you don't find a tree as a general purpose container most often is because there's so many different ways to implement them. There's no way to build one tree to rule them all, or one implementation for the container that would satisfy everybody. So in a vector, in a list, in an array, it's pretty easy to give people something that everybody's going to use pretty reliably. But with a tree, this is something that I didn't really understand for a long time. With a tree, there's a million different ways to do it, and there's like unique things that you might want to do. It's the same thing with a graph, and building the stuff is pretty straightforward. So it's not so hard. And when you do want a specific functionality, like a dictionary, then those things are available, but not just a tree. So yeah, that's about it for the data structures and kind of review. And yeah, so we'll now get into some of the cool, more physics stuff, but that's going to be mainly done with online videos that are going to be provided to you in the course.